Okay, um, so hopefully we're all in the same room because it's worse for me than for you. There should be algorithms, right? Yeah. There's supposed to be like 150 of you, but I don't really believe that. Uh, okay, that's fine. Um, okay, so let's get started. Okay, so I'm Kent. You can just call me Kent. Uh, every year I realize I do the same lame thing. On the first slide, I put up these ancient people and ask if you know who they are. Yeah. So does anyone know who the person lady is on the left or the man on the right? Yeah. Okay, Ada Lovelace. Good. Uh, all right. So that's one down, one to go. Yeah. Or any. All right. Alan Turing is the other one. So Alan Turing, maybe well, he's had a whole movie about him. So by now, uh, but before Alan Turing, actually Ada Lovelace, back when there was this crazy guy named Babbage who like tried to make some kind of mechanical light calculator. I think he was just trying to do like logarithmic tables so they can figure out like literally where cannonballs land or something. But he was making this big steam powered thing, and he happened to know Ada Lovelace, who actually started thinking about, I think, certain geometric problems that can act at least, writing down on paper, sort of like algorithms, some kind of step of instructions to solve things. That was still pretty novel, kind of conceptually novel. Uh, her father also, Lord Byron, is a pretty well known author, but maybe not the best dad. Um, Alan Turing, of course, you all know well. He was a hero of World War II for decrypting the German Enigma. But before that, when he was actually closer to your age than mine, um, he answered a very deep question. So David Hilbert, a well-known mathematician, around the turn of the century, asked, at some level, like, do all logical questions have answers, or a more particular form is kind of, is everything computable? Is there anything that's not computable? And Alan Turing was able to say, okay, there are things that aren't computable, and he wasn't the only one to do it. Alonzo Church did it a year before, but Alonzo Church was really a older mathematician, and he did really like a pure math proof. It's not super fun to it's very abstract. Alan Turing's approach was very interesting because he first kind of proposed a mechanical thing that looks a lot like a computer today, something that basically has RAM and you look things up and you follow instructions. He says, well, in this model, there's things you can't do. Okay. So he was answering a math question, but he ended up proposing this computational model, which then, von Neumann kind of bases some of his plans on and things like this. So these are maybe two theoreticians who have had some, whatever, lasting impact. Okay. Same lame story every year. Um, All right, so let me get the bureaucratic stuff out of the way first. Um, the most important thing is that we have this website called fundamentalalgorithms.com. I actually forgot to update my personal website's link to it, but it's easy to remember. And it's a massive PDF, and we just try to put everything in there, like everything, the lecture notes, the links to this video, the homework, the syllabus. It's the best way to keep everyone on the same page. We're doing this in sync with Mike Atala's class. He's been very gracious to kind of go along with us, so they're following along too. So if you have friends in that class, we're all doing the exact same thing. We can mix up PSOs. That's all fine. Our TA meetings are all joint. Um, but the key point is we just try to put everything on this PDF. If there's some confusion, you find some issue, then let me know so I can update the PDF and immediately everyone is up to date. Okay, so that's sort of like a source of truth. Um, Maybe the most important part of this page uh, is our set of TAs. So we have not technically a ton. We have like 30 something, 8 graduates and 24 undergraduates, many of whom I've taught. So I know they're spectacular. And I think a lot of them are here. So if you want to stand up or raise your hand or something, I think they just want to say hi and they might run away. But I think COVID and Mukul, Akash, Ridu, Ethan is in the back. Dia here, you should raise your hand or something. Otherwise, you're indistinguishable. Uh, am I missing someone? Oh, Leo and Wilbur in the back. Okay, so that's just some. Uh, but anyway, They're going to be well, just incredibly valuable. The only tough part about this class is that there's a ton of students to a relatively small number of professors. But luckily, we have all these, mini professors uh, who can well figure everything out basically. So they will have office hours, of course. We're planning to not start office hours until next week because we don't think you'll care about the homework until it gets closer to being due. I'll still have office hours, and Mike will as well for this week. And they'll also be running what we call PSOs. But at some level, we're just going to come up with like a worksheet of problems that we can work on together. They might go through it at the end of the class with the students or something, whatever. It's kind of up to their discretion to figure out how to turn it into a nice class. But it's going to be a little bit more active than what we do today, which is a little bit more me talking. I mean, I'll try my best to solicit some stuff out of you, but PSOs is really where you, I think, yeah, get better attention in some ways. So I strongly encourage you to take advantage of it. And we're never going to take attendance or anything, but in classes past, there's certainly a strong correlation, uh, between grades and stuff. Um, Homeworks are also listed, or be weekly homeworks. Yeah. Okay. Um, so in the back of this book will be the syllabus. It has all your standard things like how much the homework is worth and the midterms are worth and things like this. I'm not going to bore you by going through all those details. So I'll ask you to read it and then I'll allot time at the beginning of the next couple classes for questions or clarification, or if you see some major issue. It hasn't changed much in the past few years, but the time to change things is now, not later. Um, yeah, the highlight and things you're probably most concerned about. Yeah, so we have great TAs. There will be two midterms and a final. We have roughly weekly homework. We have policies like uh, at the end of the day, you have all these scores for all these problems, and we'll just drop the lowest 20%. So if you bomb some or like, some pet gets ill or something like this, that's just like a catch-all, for all these things. Okay. Um, And then also at some level, it's partly because, we give homework and it's a chance for you to learn, a chance for you to try. And we're not really trying to punish you that much for getting this or that right or wrong. So that's also partly, just to take some edge off of it. Um, we also have a unique late homework policy. Okay. So I think for every homework, yeah, I think we'll have a late deadline that's maybe 3 or 4 days later. I'll double check, but it might be like homework's due on Thursday, and then the late deadline's on Monday. But between Thursday and Monday, we'll actually put out the solutions. So if you really want, you can look at the solutions, and if you bomb the question, you're welcome to update your solution and submit it. There will be some fixed number of points we take off, like maybe 3.5 or something, so you can assess for yourself. Okay, and we certainly don't mind because it's easier to grade the correct homeworks than the wrong ones. Okay, you're also allowed to do homework in groups of I think up to 3, I believe is our policy. Things like this. We also don't mind, yeah, if you decrease the total number of submissions. We have a grade scale set up, but I forgot to put the link in the syllabus, so that'll come up soon. And there'll also be multiple choice on a weekly basis. Okay, that will have to be done individually, but that'll be obvious from the website. Okay. Um, I assume no one has read the syllabus, but is there any questions I can take now? And again, we'll just do this for each of the next couple classes. Okay, let the fun begin. All right. Okay, so today's sort of so yeah, the TAs don't of course have to stay. They've already taken this class or something. But in any case. All right, so today's the first lecture. So I'm expecting a lot of what we cover you've already been at least exposed to before. Don't worry, the class will pick up plenty fast enough. Uh, so okay, yeah, I guess the premise is that you already know quite a lot about theoretical computer science, and I'll go through two basic examples. So, all right, so let's just start really small, counting. By the way, am I audible in the back? Is this okay? Good. Okay, so counting, right? 1, 2, 3. How high can you count with your fingers? 10. Okay. Can anyone do better than 10? All right, 2 to the 10. How do you get to 2 to the 10? Okay, so the trick, of course, is that every finger, right, is some bit, right? And so you can make various things and come up with 2 to the 10 combinations. Anyone do better than 2 to the n? Yeah. Oh yeah, some people have thought about ternary and trying to do some half weird thing, although I don't have the dexterity, I think, to do like more than one finger at a time. Any others? Sometimes people like flip the hand. I guess if you can blink, you can basically do Morse code, but like anyway. Okay, but you get the point. And okay, so how many tallies are on the left? 23? Somehow 4? Uh, the truth is, I don't think anybody knows. Okay, in principle, there was supposed to be 23, but I think the point is clear. This unary system is a very inefficient way, to describe quantities. Yeah. So the right hand side is much more efficient than the left hand side. Okay. And and of course, you already know the answer to this. In general, when you have something like decimal notation, if I have 5 digits to work with, how many numbers can I express? Oh, Madav's here too. Yeah. 5K digits. How many different numbers can I express in decimal? Don't be shy. Yeah, 10 to the K. All right, so 10 to the K. Of course, you already knew this. Okay, but this is still very important, right? Because it reflects a combinatorial explosion, right? Every time I add one more decimal, the number of possibilities, blows up multiplicatively, right? This is something that represents like a lot of complexity. You're able to enumerate a lot of stuff was very compact. Okay. All right, so that's one side. So you already understand this, of course, because you understand counting, you understand numbers. Nothing new. Okay, here's something else that's like equally juvenile or belittling or whatever. Okay, so when I was a kid, like in third grade or something, the teacher would play this game called Over Under. The teacher would think of a number between 1 and 100 and keep it in their head, and we couldn't go out to recess until we figured out the number. Okay, which was very important. I felt just as probably you feel now, and but you would be able to guess a number. Teacher would go over or under, and then based on that, I would guess something bigger, guess something smaller. I mean, not just me; the whole class is kind of yelling at the same time. Okay, so I assume everyone's played this game before. Probably all the Americans at least. Okay, so um, okay, so let's play. Just shout out a number, and I'll tell you over under, and I'll write on the iPad to keep track. All right, 50. Over. Okay. Under. 60. Okay, make up your mind. Okay, the next guess goes 67. Okay, under. Under. Guys are very mediocre. Over. Over. Under. Under. Okay, 55. So it took you guys 9 rounds. Okay, but good job, you got it. All right, so that's the game. Very simple game. Over under, right? Okay, so obviously, the very slow approach would just go 1, 2, 3, 4, 5. You would get the answer. There's no issue about correctness. It's just that you'd have to go through all 100. But all of you realize that you should start at 50. Why? Like, obviously, I'm not going to think 50, right? So what would, yeah, it eliminates the most. And to be more precise, it's not because 50 is the average, it's because it's the median, right? It's right in the middle, and it'll cut off half of your options. Okay. So what you should be doing, I think we went a little off track, right? If it's under, you go to 25, it's over 75, right? This kind of simple tree. Okay, something like this, and you keep going down. Okay, so good. All right, so the question is, how many rounds, if it's between 1 and 100, do you need? Or maybe the exact number is hard, but you can think of like how you would express it. Log 2 of what? Okay, so log base 2, is that all you also had in mind? So log base 2 of 100 for us. What is log base 2 of 100? You should know your powers of 2, you're computer scientists. Yeah, a little under 7. Why a little under 7? 128 is 2 to the 7, and 2 to the 6 is? 6. There's got to be something in between. So it turns out to be 6.67, I guess, according to Google. Okay, so how many actual rounds do you need? If you have to output a integer number. In particular, is it 6 or is it 7? And why? 7 because you don't reach it at the 6? Yeah. Sorry? I guess there might be some ambiguity about the last question. Okay, but here's at least my logic. I had 6 in mind, but I might be off by 1 because that's what I do. But if you half 100 6 times, you'll get some number less than 2. And the only integer less than 2 is 1. Now, there's some ambiguity about whether you need to guess the last one or so maybe that's where the off by 1 comes. I'm not sure. Okay. In any case, we will never care again about being off by 1. Okay, but it's just for fun. I thought it was 6 rounds, but then what is a round is kind of ambiguous. Okay, so these are, of course, 2 examples of very simple mathematical functions, which I'm sure you are quite well aware of. One is exponentials, right? When I say 2 to the n, I'm multiplying 2 n times. It's growing rapidly. And the other side, we have logarithms, right? Before we had logarithms base 2, that's basically how many times you have to divide by 2 until you get down to 1, starting from n. As a silly looking mathematical identity, it's whatever value gives you 2 to the log 2 of n is equal to n. Okay, so it's the inverse of exponentials. It doesn't have to be base 2. There's that magical Euler constant, right? That's called the natural log. Log base 10 you often see in the wild, but it could always be any value b. Okay. Often we won't worry about the exact value b for moments I'll get into momentarily. Reasons I'll get into momentarily. Okay, so all right, to further drill this point about big and small functions and things like this, how many atoms, maybe you know, or do you think are in the universe? N to the 23rd? Oh, 10 to the 23rd? Okay, that's one guess. What's amazing is that they can estimate this. Yeah. 10 to the 46th? Okay, any others? Maybe I'll write it down. Yeah, keep going. 23, 27, 46, you said? Any others? How many zeros do you need to express? These are all 10 to those. No one else has any interest in, no guesses? I can force you. All right, let's take, all right, how about this? All right, you have 4 choose places to vote. You either think it's smaller than this, one of these gaps. Yeah, I'm gonna get you guys to raise your hands. All right. Oh, actually, and then let me do the first meta vote. Who's not going to vote? So you get to choose either less than 10 to the 23rd, between those two, or bigger than 10 to the 46. But who's opting out now? Who's not going to vote? Okay, one person who suggested one of the numbers. Okay, 2 of you are not voting. Okay, who thinks it's going to be less than 2 to 10 to the 23rd? None? Who thinks it'll be between 10 to the 23rd and 10 to the 27th? None? Who thinks it's between 10 to the 27th, 2 to the 46? Okay, now we're getting some participation. Or maybe it's because you're running out of options. Okay, so I'll put that like 87.5%. Okay, who thinks it's gonna be more than 10 to the 46? Oh, these numbers won't add up. Okay, this will be like 22%. Okay, and who didn't vote but didn't say they weren't gonna vote? Okay, one. Okay, so the answer, it turns out, don't ask me how they figured this out, is I guess 10 to the 82. Okay, so it's actually way more than any of the guesses. And this isn't like twice as big as any guess, right? This is 10 to the 40 bigger than our biggest guess. So it's like almost squaring our best guess. Um, okay. All right, so there's a lot of atoms in the universe. What is the log base 2 of the number of atoms in the universe? Yeah. Okay, so we have something like this. We can pull out, oh, it's not coming back. Okay, we can pull out the 82, right? This kind of thing we did in high school. And then what's log base 2 of 10? Or what's it roughly between what and what? Should be between 3 and 4. Apparently it's 3.32. Okay, so we put that together, we start getting something like 272.3. Okay, so there's 2 to the 272 atoms in the universe. All right, big number. What is the log of the number of atoms in the universe? So I think first we just plug in log base 2 of 272.4. Now, what is the log base 2 of that? Somewhere between 8 and 9. Yeah. Okay. 8 point something. I obviously could have looked it up and didn't bother, so that tells you how much I care. But the real point is that you can take literally the most astronomical number I can think of. You take the log twice, and now you have something you could count on your fingers, the crude way. Okay? So a logarithm is a very dramatic number or function. Okay. Yeah, you already know this stuff. Okay. The point I want to make, though, is that at some level, this class is about trying to distinguish these two regimes. Okay? So on the left, we have something that's growing very fast in complexity, 2 to the n possibilities. Each additional piece of information doubles what you're trying to deal with. Okay? This is an intractable situation. The right-hand side, binary search, with every operation, you may be able to eliminate half the options or something. Right? You can get to your answer super duper fast, whatever you're looking for. Okay? So one way to think about it is like this. The left-hand side represents essentially no structure. Right? You can't say anything or eliminate any of the combinations. There's no structure. It's just enumerating stuff. Okay? Something like binary search, the numbers in order between 1 and 100, there's a ton of structure there. You can make very strong statements like if I guess 50, I eliminate half the options. Right? That's something you know completely well. Right? And you can basically do whatever you want in whatever time you want. Okay, so left-hand side represents kind of a lack of structure and intractability. The right-hand side represents structure, things we can actually compute efficiently. Okay, and we'll often look at problems and try to figure out which category it falls into. And that'll really kick in midway through the semester, but there's simple-looking problems that are quite hard, and quite hard-looking problems that actually have very elegant solutions. Okay, all right, so, okay, so much for that. Any questions? I don't know what questions one could have. All right. Well, it wouldn't be a generic algorithms class if our first kind of real topic wasn't sorting. Okay. I assume everyone has probably done some sorting before. At least that's what everyone tells me. Okay. That may be the case, but we can still at least, establish some habits that'll be useful when things pick up. Okay. So I'm going to kind of teach as if you hadn't learned all this stuff before. Okay. So let me erase this. All right, so in general, your input, it's always good to state the input and the output. So your input is like, let's say it's in general n comparable elements. Here we'll just use numbers. Okay, you have n numbers and your goal is to output a sorted list. So again, I'll force you to participate by reading off this sort of list for me. Okay. Or maybe first let me do it graphically. Your input's going to look like this. You want your output to be nice and clean. Okay. All right. So let's just go through and you just shout out the next number. I'll write it down and we'll act like we're having a good time. Okay. So what's the smallest number? Okay. I'll check it off for you. What comes next? Oh, unison. Excellent. Keep going. Okay. Next. Next. Gee, that's creepy. All right. Next. Okay. Next. Yeah, I got a double in there. All right. Next. 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 And then finally, okay. All right. So we all know how to sort numbers. Great. Well done. That was the best ever. Truly. Usually it's like literally two people, and I just feel bad for them more than anyone. Okay. So when we typically sort numbers, like literally us, what do we do? What do we ask ourselves first? Yeah. Yeah, we asked ourselves what came first, right? I think that's the most human thing to do. We ask ourselves what comes first. I mean, granted, I was kind of prompted, but we asked what comes first, and that was one. And it's a little bit easier if you kind of check that off so you don't get confused next time. And then what did you do? Yeah, you say, okay, what comes second? That was two. You checked it off. Yeah. Okay, so that would be a simple sorting algorithm. If you were like sorting a bunch of mail at home or something, it's probably what you do. Uh, Actually, you would never sort mail at home anymore. Okay. Every year more analogies slip out of my grasp. Okay, so this simple algorithm, sometimes I think called selection sort. The question is, how long does it take? Okay, we can break this down. So at some level, we're just building the sorted list from beginning to end. With each successive number we pick, we go through the whole list and find the next one. Yeah, simple algorithm. Okay, so one way to account is to break it down as follows. How many kind of iterations do we do, outer loops, if there's n inputs? N. And then for each of those iterations, roughly how long do we spend on that iteration? N, because we're roughly scanning the list. Okay. All right, so for n iterations, you spend roughly n time. And what's our overall running time? N squared, just multiplying them together. Okay, good. So nothing mysterious. Okay, so we're going to call that in our class big O of n squared. I assume everyone's been exposed to big O notation before? Okay, so the formal definition is almost misleading. It says that, look, for sufficiently large n, it's going to take out some constant times n squared. Okay, there exists some constant, there exists some sufficiently large regime. Okay, that will be the formal mathematical definition. Okay, but it's a little bit besides the point. So first of all, when we say steps, what do we even mean? Right? And of course, this varies on 100 million different things. What computer you're running on, what programming language you're using. If you're programming Python, maybe a factor n slower than you expect, right? So it's not really clear what you mean by step. Okay, but on the other hand, I think we're quite clear about the algorithm. We were all thinking in some way that was completely independent of the algorithm. I mean, of the language, of the computer. There's clearly something there that's not so dependent on these low-level details. Okay, and that's really the point of big O notation. Low-level details, if you get a CPU that can inline some steps, it goes twice as fast. Okay, your C divides by 2, but really your algorithm behaves asymptotically like n squared. If you double the input, you should expect the running time to go up by a factor of 4. Okay, at least in the interesting regime when n is large. If it's n is small, who cares? Okay. And the real point is by hiding the constants, right? We're really abstracting out the stuff that we don't care about, that don't really matter, that aren't at the essence of the problem or whatever problem is under consideration. And what that does for you that's really important is it gives you a clean space to actually develop some kind of more unified theory of algorithms, right? If we're running around worried about constants all day. We won't get anywhere. And I won't come up with anything that, is sort of general. Okay. So the big O notation is not so much about the formal definition. It's about being able to tell the forest from the trees. Okay. And really be able to get to the high level bits, the highest order bits. Okay. All right. So, okay. But of course, you've all seen big O notation, and we'll get so much practice that this will not be any kind of bottleneck. Okay. So, human sort takes n squared time. And in algorithms, always the question is, can you do better? Okay. Of course, you all probably know the answer. But let me first discuss a little bit as if you didn't. So n squared is in some ways coming from comparing, or you can think of n squared as comparing every pair of numbers with each other. Okay. And at some level, when we say, can we do better than n squared, we're sort of asking this question of, can you sort n numbers faster than comparing every pair of numbers with each other? Okay, you probably know you can do better, but a priori, that's sort of an interesting question. So do we really need all comparisons? Okay. So let me give a slightly different perspective. Again, this might feel overkill just for sorting, which you probably learn every class, every semester. But the general steps we're taking, the perspective is one that we may be able to reuse in more novel situations. So besides, these questions where you ask to solve something, find something, there's often questions of verifying something. Some question you don't know the algorithm for it. One thing you can always ask yourself is how long it would take to even double check a supposedly correct answer. This question of verification. Okay. So suppose you were given a list of n numbers. Okay. How fast can you verify and check that it's really a sorted list? So this is just a yes or no thing. How long would it take to verify that it's sorted? One lazy thing you can do is you can use that human sort we just used, spend n squared time, and then compare everything one by one. But what else could you do? Yeah. Okay, you can maybe do it in one pass. How could you do it in one pass? Okay, so imagine I'm a computer. What should I do? Okay, so you're going to go pair by pair and say, okay, is A1 less than equal to A2? Yeah, so you check that. You go to the next pair, is A2 less than equal to A3? Check that. Is A3 less than equal to A4? Check that, right? And if you go all the way through, the whole thing is sorted. I mean, the fancy word would be because of the transitive property, right? If A is less than B and B is less than C, then A is less than C. Okay, so you have some structure there to let you get away with this. Okay, but it only takes one pass. It only takes, what would be the time? Big O of n, right? Some constant time for every element. Okay, good. All right, so then at some level, we have two possibilities. Okay, I'm assuming we can't do better than big O of n. And so we're sort of in between. N squared, we can do at least that well. We probably can't do better than O of n because that's the best we can do to even double check an answer. Is it in between? Can we get it down to big O of n? Or are we stuck at n squared? Okay. Okay. You all know the answer to this particular example, but that's the kind of question you can ask of any problem. So, okay, work with me as I do my pedagogical thing. So as we build up towards a better algorithm, let me give a special case that's a little easier than sorting completely unsorted list. Suppose I gave you the input divided into two lists of roughly equal size. Actually, maybe that doesn't matter so much. But anyway, two lists that are sorted, and you just want to combine them to output a sorted list. So I give you as input two sorted lists, and you want to output their combined sorted list. How fast can you do this, and how? Okay, O of n. So how? What would I do? Okay, so this is not so different than our human sort. Our human sort was always trying to find the next smallest number. But here we know that's always at the top of one of the two lists, right? What's the smallest number? What's the smallest on the left side or the smallest on the right side? So we just need constant time to compare two numbers instead of having to compare n. Okay. And then once, we wrote down one, we can check it off. And now when I want to find the next smallest number, I know it's either the second one in the first list or the first one in that second list. Okay. So by keeping a pointer at the beginning, we can gradually work our way through because we always have this small subset where the next smallest one is coming from. Okay. So this is sometimes called merging. Uh, this would be pseudocode for it, which I feel like makes it look way more complicated than it really is. Okay, I'm just allocating an array. I start with pointers at the top of the two input arrays, and I'm just comparing the two, comparing the two, comparing the two, advancing the pointers along, writing to the output array. It's not even worth mentioning, but people often forget that at the end, you might have finished processing one array, but you have some leftovers in the other, so you need to copy all those over. That doubles the length of this code. Okay, good. So, but what merging sets up for us is a very nice divide and conquer algorithm, right? Because now I actually know, okay, sorting a completely unsorted list of problems, that's some problem, some kind of issue. But I do know that I can actually put together a partially sorted input, two sorted lists very fast. Okay. So then an idea might be as follows. Let's just divide the input in half, somehow sort the first half. We'll figure that out later. Somehow sort the second half. We'll figure that out later. And then let's merge the two halves together. So I know I can deal very well with two sorted half lists. Let's just try to get to that point. Okay, so I'm going to divide the input in half. I haven't really done any real work or thinking yet. Just kind of divide it half. And then I know I'll be able to merge it back together. The only issue, of course, is how do I sort the two halves? Yeah, and it feels a little bit like cheating because this was the original problem, right? At some level, you're like, oh, how do you sort? Well, you sort this side, you sort that side, you put it together. Doesn't really seem like I actually taught you how to sort. Okay, so what's the missing buzzword? Yeah, recursively. Okay, so we are going to do just that. It's not going to be anything more than sort the first half and sort the second half. You might have to be a little careful when you're down to one or two, but by then I think it's pretty easy to sort two elements. Okay, but this is exactly what we're going to do. How do you sort? Divide it in half, sort the first half, sort the second half. I won't be any more specific than that. And then merge them together at the end. Okay, and that's a full description of an algorithm. I left out the base case because I'm a little lazy. Okay, so that is a divide and conquer algorithm insofar as we're dividing the input, conquering the two halves separately, blah, blah, blah. Okay, so how do we, okay, I didn't want to show this. Okay. Okay, so the real question is, how do you actually design a recursive algorithm? Or how do you justify something like this, which may feel like cheating, right? How do you sort? Oh, you just sort the two halves. Okay, is that cheating? So what the key important thing, I'm hiding the next slide because I forgot to actually hide the answer and I want to try to solicit this out of you, is to define a clear and really rigorous recursive specification. So what do I mean? I mean, we want to be very clear about the input, and then we want to be very clear about the output. Okay, and we'll expand on what we mean by clear. But this also sets up a contract. First, what are you trying to implement? But two, what can you rely on in the subcalls? So if you set up a formal contract, then you can actually call on it recursively, knowing that that contract is going to get fulfilled. Okay. Ultimately, you can't prove any of these algorithms work without something equivalent to a recursive spec, which is called an inductive hypothesis. We're making explicit what would be implicit in anything that's correct anyway. Okay, so you always have to do it in this class. So, so for this problem, then let's try to come up with a recursive specification. Okay, so I'll just give it a name, sort, and then maybe it takes as input an array, right? Something like this. But something here, I'll give ourselves more space. I'm imagining writing out some kind of sentence that clarifies what A is or something, and then is very clear about the desired output and the structure of the output and things like this. So but ultimately, it's just a sentence. It might be a slightly clumsy, awkward sentence, but it's just a sentence. Anyone want to give it a shot? Well, okay, but that's more like a phrase. You know, imagine you're actually writing them. This is also a very practical thing to do in the real world. You're implementing something, you should define a clear interface. Then the person you hand the code to doesn't have to look at your ChatGPT written code. Specifications may become more important in the future than the stuff that's going inside, right? All right, so who wants to try to capture what we're trying to do in a sentence? You can use words like sorted. We know what sorted means. You don't have to re-explain that that means all the numbers are increasing. Yeah. So what I want to think of this whole function as my sorting function. Okay, so we're not really trying to describe the whole algorithm. We're just trying to describe the input-output kind of interface in a formal way. And then that will become formally useful because then it'll kind of really lock in what we're doing when we call it recursively. Because so just what's the input, what's the output? Yeah. Yeah, given a list or array or whatever of and numbers. I guess generally we're doing comparable elements, but numbers is fine. Output what? The list in sorted order or something. Whatever. There's 100 different ways to say it. So it's nothing special. But you are making it very clear what you're taking in. You're very clear what you're giving out. First, it's a list, right? That's the structure you should expect, but also it's sorted, right? And that's really important because otherwise you wouldn't know what you're getting back here. You really need to get a sorted list back in your subcalls to be able to merge. Okay. So that's what we call a recursive spec. It's not really much more than that. I guess this is what I had prepared. And it's roughly the same thing. Okay. All right. So why do we have a recursive specification? I guess I have three reasons. I've already said them out loud. Or one, it's always good to say what your input and output is. Just always do it. It makes the grader's life easy. Just always do it. Wherever you are, walk in a room, say, hi, my name is this is my input, this is my output. Okay. Two, it creates this contract that the algorithm must fulfill. First, that gives you like a target. Okay, I need to implement this, and then it puts you in a certain kind of focus state. But then, crucially for our recursive algorithm, it creates this contract that you can rely on for all your subcalls. Okay, you take your big problem, you make it smaller. It doesn't have to be that much smaller. Here we're dividing in half, so that's quite a bit smaller. But anything slightly smaller, induction is valid, right? Modulo the usual mistakes people make was induction. Okay, and at some level, you're able to take big, complicated problems and turn them into slightly smaller problems, and then you're done. Yeah, and you just nibble away at complex things. And then lastly, I don't remember what's here. Okay. If you're going to prove any of these algorithms work, these recursive algorithms, you're going to need a proof by induction. And you're going to need an inductive hypothesis. The recursive spec is your inductive hypothesis. In fact, I think for, on homework 0, we're going to have a list of problems where the goal is to just get you all to do a lot of problems rapidly. So we're not going to ask for all the details and all the proofs, in full rigor, but we will ask for a recursive spec. And what we're going to do is we're going to read your recursive spec and say, is this strong enough to be extended to a proof by induction? Okay. And in this way, you don't have to write out the whole proof and you can just go through a lot. It's more fun that way. Okay. But the recursive spec is your induction hypothesis almost always for a proof by induction. And if you don't have that straight, then you don't have a clear, correct algorithm in your head anyway. So this is just making explicit, bringing to surface something that you have to do. Okay. Okay, good. When did this class end? At 45, 240? Okay. Okay. So once you have a recursive spec, the second step is to implement it. As usual, I feel like the typesetting makes it look more complicated than it is. I can go through it slowly since it's our first class. Okay, base case. If there's only one element, I wrote n less equal 1, so I don't even have to worry about no elements. Just return the array. It's already in sorted order. Okay, base case is usually not very complicated. Just you might accidentally skip it. If you want it to be really safe, you could wrote if n is less than equal to 5, use human sort. Yeah, it takes n squared time, but 5 squared is nothing. Right? You can brute force any small n, then you don't have to worry about being off by 1. Otherwise, I pick some index that's in the middle and over 2 rounded down. Here I started indexing from 1 to n. I made that clear in my input. And otherwise, I recurse on indices 1 through m. I recurse on indices, that's not right. Oh no, that is right. M plus 1 to n, and then I merge them together. Okay. Again, I feel like this is only confusing. I'm just sorting the first half, sorting the second half, merging them together. Okay. All right, so yeah, we're just gradually going through the steps of our first kind of algorithm we're doing together. Yeah. Okay. And then the remaining step or the next critical step is trying to prove the thing is correct. Okay. So how would you prove it? So recursive algorithms like this, I'm sure you've already had some practice, maybe in a previous class before. We would prove by induction on the size, at least in this case, of the input. Okay. So at some level, I just want to prove the recursive spec for a given n. Okay. So for some input of size n, I want to prove that this algorithm really executes and fulfills that recursive spec exactly. Okay. Well, if n is equal to 1, then it's already sorted, it's correct. Now, why do you even have to write this? I don't know. If n is bigger than 1, then we're going to divide the input in half and recursively sort the two halves. And here's like that one italicized sentence, by induction on the input size or by induction on n, by induction blah, 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 the recursive calls will return, those inputs in sorted order. And then, well, here, let's just take for granted that merge is correct. And merge is able to take as input 2 sorted lists and output 1 sorted list. Okay, and that's mostly it. If you have the right recursive spec, the inductive proof is almost boring. There's often little more to be said than roughly regurgitating the spec like 3 times. Okay. But sometimes there's some details. Okay. I think the really key point is that the recursive spec is for all practical purposes, your inductive hypothesis. Okay. It's really the backbone of all the correctness. All right. Okay. So I once drew this picture. I thought it was cool. You can envision the algorithm, if you really wanted to like unroll the whole thing, as doing something like this. You start with the input on top, you divide it in half, that gets divided in half, that gets divided in half, that okay. Somewhere at the bottom, you get to the base cases, and then this starts to become sorting and you start merging things together. Yeah, so if you actually want to unroll the whole thing and try to envision the computation, it would look something like this. Okay. But frankly, I think this is actually just confusing. You should just believe in induction and just say, it's sorted both halves correctly, and you're done. Okay. But the next question is, I think the final leg for this particular problem is analyzing the running time. Okay. So we kind of want to figure out roughly how long this crazy looking computation is actually going to take. Okay. So how do we do this? So the first step is almost the most important one. It's just trying to model the running time. Okay. So first, I think the first step is just say, okay, I'm going to define some function t of n. T of n will be an upper bound of the running time of my algorithm on any input of size n. T of n now has some meaning, and then I can start modeling my algorithm. Okay, so T of n, that's going to upper bound the running time on an input of size n. Okay, all right. Now, for our function, as you guys know, this is called merge sort. For this algorithm, oh, actually, okay, that's good. Okay, but now we want to actually start doing some math, and we need to start actually modeling the thing. Okay, so eventually we want to get some concrete, really close form thing for T of n, but first we want to start modeling things where we just look at the description of the algorithm and try to model it. Okay, so does anyone want to try to take a stab? Where might I start? Or you can ask, what's the easiest part? Huh? Okay, so merging takes n time. Okay, I've got that on the bulletin board. Yeah. Yeah, maybe the base cases, right? So things like, you know that t of 0 and t of 1, you can throw t of 2 if you want in there. This is some constant, and I'm just going to write 1 because I'm not too concerned about which constant. Okay, it's going to be understood that everything in here is up to a constant. Okay, so almost always the base case will be a constant, because even if you did the worst possible thing, there's only a finite number of things you can do on input of size 2, 3, and 4. Okay, the more interesting part is general n, right? So now you have n is bigger than 1, and you want to start modeling T of n. Yeah. So there's two recursive calls, each acting on half of the input. Okay, two recursive calls, each acting on half of the input. So if I'm going to be pedantic, maybe on first pass, I'll write it like this: rounding up and rounding down in case there's an odd number. Okay, so that's our two recursive calls. So the great thing is that now that we've defined T of n, it has a meaning. T of n over 2 has meaning. Okay, so you just have to define the thing, and then you can start playing these games. Okay, but what else? That's not the whole thing. We don't just do two recursive calls. Yeah. We also merge. How long does that take? N. Okay. Now, for all practical purposes, okay, so if n was a power of 2, then we would have just written 2tn over 2 plus n, right? Because there's nothing lost. Okay. And for all practical purposes, you can write something like this, and there's various tricks to justify it. Okay. So for example, well, I don't know if it's worth going through the tricks. You know, if T of n was defined as an upper bound on the time, right? If I'm given any generic n, I can always write T of n is less than equal to t to the whatever is the power of 2. Oh, one sec. Let me add this one trick. Of size at most n. So I'll say T of n is the worst case running time over all inputs of size at most n. Of course, we're interested in n. It should get bigger with bigger n, but I'll write less than equal n just for formal sake. This way, if I'm looking at some generic n, and I want to bound T of n, and I'm worried about this round up, round down, and these details, right? I can write T of n is less than equal to 2 to the rounding up log base 2 of n. I'm just taking n to the next power of 2, and then whatever clean analysis that's much easier to work with powers of 2 in this example will just apply. Okay, there's also other tricks. But basically, you don't really need to write out that first line. You can just give us the second line. It's kind of understood, and you're not going to lose anything. Being off by 1 is not going to matter no matter how you look at the math. Okay. There's other ways to get around this. Okay, so we have now this. T of n is equal to 2tn over 2 plus n. That models our running time. I make two recursive calls. That's however long it takes to sort inputs of half the size. And then I spend linear time merging afterwards. Okay, so now the question is, how do we solve it? And here's how we're going to solve it in this class. So we're going to use something called a recursion tree, which is a very simple thing, and it's going to suffice for everything. And if you really want to push the recursion tree, you can capture all the fancy things. Okay. So, but one thing I like about recursion trees is it makes it very easy to also visualize the algorithm and visualize where the work is going. And I think that intuition is actually helpful when you flip over to a space where you're really trying to design algorithms. Okay, so what we do is I first start creating a tree where I sort of think of each node as one of these subproblems. Okay, it's a binary tree because here we have two subcalls. And the first thing I do, I don't think too hard. I just annotate how large each subproblem is. So the root will have subproblems of size n. Okay, that's the starting problem. How big are the children problems? N over 2. And if I go below that, n over 4. Okay, so it's going to keep going down by powers of 2 until at the bottom, you're going to get a bunch of these base cases of size 1. Okay. And then the next thing I do is I start tallying up how much work first I spend on each problem, and then I'm going to add them up layer-wise in the tree. So take this original problem. So how much work does it do excluding recursive subcalls? So recursive subcalls are going to be accounted for lower in the tree. So how much other work am I doing sort of at that root problem? And what am I doing at the root problem besides the recursive calls? Merging for O of n time, right? So I need O of n here, right? I could have just wrote n. And then likewise, the subproblem, if I look at this one here, it's going to have two recursive calls. And besides that, it's going to do some merging in roughly n over 2 time. Okay, n over 2, n over 2. Here it's pretty simple because it's just linear work. In general, everything today, well, it's just lecture 1. So, okay. But now what I'm going to do is I'm going to add up the total amount of work level by level. So the top level, there's only one term. The total amount of work was n. Okay. The second level, oh, I can't even do that right, has two problems, each giving us n over 2 work. Okay. What does that add up to? N. What about the third level? Okay, so you can see that in general, you're going to have some 2 to the I times n over 2 to the I all the way down. Okay. So everything's going to be n all the way through. Okay. And if we tally everything up, we'll get the total amount of work, the total amount of time in the algorithm. Okay. So if I just know how tall this tree is, then I just multiply that by n, and I'm done. Okay. How tall is the tree? Log base 2 of n. So we get n log n, just like that. Okay. We're just adding things up. The tree makes it very easy to account for all the work. Okay, it just lets you visualize the recurrences. At the end of the day, it's just arithmetic. You'll get practice with slightly more tricky ones in the PSO, but what you'll often see is like what ends up here is either a geometrically increasing sequence or a geometrically decreasing sequence, and those aren't so hard to deal with. Okay, but you're just adding things up. I think the key point is figuring out the right way to kind of see it. Yeah, any questions? You'll get a lot of practice. Yeah. Yeah, so in another example, it might have gone like this. N 3/2 n 3/2 squared n 3/2 cubed n. That would be a geometrically increasing sequence, right? And then somewhere down at the bottom, you're going to get, let's say that this is the height of the tree, some h. You're going to be summing up from, no height all the way up to h, 3 over 2 to the h n. Okay, so that would be a geometrically increasing, not h to the I. I is just going from 1 up to 8. Maybe I could have started counting from 0, but that's not so important. Okay, so the terms get bigger and bigger and bigger and bigger. Okay. Does anyone know what the answer is? 3/2 to the how to sum a geometrically increasing sequence. Does anyone remember like vaguely doing this in high school? And there is some formula, right? And if you had scratch paper, you could probably figure out exactly how to do this. Okay, but there's a much easier way to do this now because of big O notation. I only care about the big O at the end of the day. Does anyone know the easy way to evaluate this up to constant factors? You'll never have to work hard, at least in this respect, ever again. Yeah. Sorry? C. What is? Oh, no, no. Well, so H could be like log n, right? If H is like log n, then this does not represent, this term does not necessarily represent a constant, right? 5 to the log n is now n to the 5. So you can't just, it's not that easy. Okay. But some of you have all these geometrically increasing sequences. Well, let me give you an example. So just powers of 2. 1, 2, 4, 8, 16, whatever. If you just want to estimate, I told you it went up to 2 to the 100. If I added up all the powers of 2 up to 2 to the 100, then what does it come out to? Yeah, I think technically it'll come out to 2 to the 101 minus 1, but it's basically 2 to the 100. The largest term dominates. Okay? In fact, any geometric sequence, so 2 feels like drastic, it goes 3 halves. If it was 1.00001, anything bigger than 1, the largest term will dominate up to a constant. Okay? So this will always be big O of 3 halves to the hn. All right, so this is a good trick to know. It'll save you a lot of time, right? Yeah, it's not just being lazy, it's about figuring out the highest order bits. If you have an algorithm that where it comes out like this, then you should be thinking, okay, I'm really being dominated by the level with the most work. That's your bottleneck, the largest H in this kind of case. Okay, good. We're making good time. All right, so that's a recursion tree n log n. And yeah, I'm not going to just do a million examples. What we're going to do is we're going to do more algorithms, for the next 2 weeks, and each time we'll get a new example of a recurrence. We'll do it together, and you'll figure it out. Okay. I think the appendix goes a little more slowly if I don't remember. Okay. It's also in the PSO. All right. So I assume most people had seen merge sort before. That concludes merge sort. We did the algorithm. We did recursive spec, correctness, running time, and login. Okay. Have you all proven lower bounds for sorting before? Some have. Hopefully most haven't, so there's some novelty to the lecture. Okay, so let me take this topic we just did and try to look at it from a different perspective. I think it's kind of interesting. So, all right, so we showed that merge sort takes n log n time. As always, the question is, can you do better? Or in fact, is this the best possible? That'll be very satisfying. If this was the best possible, we can all go to sleep. So, or maybe you're already there. Okay, so our goal is to prove a lower bound for all sorting algorithms. Okay, and this is a bit unusual. Or it's weird for the following reason to me. If I want to get a certain upper bound, I just have to give you one algorithm that achieves its upper bound and prove this algorithm works this. And then okay, sorting takes n log n time because there exists n algorithm. When you do a lower bound, the quantification is different. I'm trying to say that any algorithm will take such and such amount of time, right? So that's already kind of weird and unusual. So it's not even clear what the first step is. So we're not trying to prove that merge sort takes n log n time. I think merge sort always takes n log n time because it always merges at each level. What we're trying to prove is that there's no algorithm that's more clever for sorting. Okay, so that's quite unusual. And okay, so we want to show that yeah, any algorithm has to take some amount of time. And here we have some notation called big omega. It's the same as big O, but it's just for lower bounds. Okay, so there's some constant, so it takes at least f of n time times a constant, at least n log n time times a constant. Now the constant may be sufficiently small instead of sufficiently large, but same deal. Okay, so I think the first step to try to prove a lower bound, I mean, at some level, I think it's the beginning that matters the most because I think the hardest thing is to try to come up with an attack, and maybe for a minute or two, I can open the floor because once I show the answer, then I can't take it back. Does anyone want to try to propose a way, at least if you haven't seen this before, of trying to prove a lower bound for sorting? Because it's an interesting question. Yeah.
We know that the verification takes at least O, then like an operations, and you probably start from there.
Yeah.
Then verification.
Yeah. So you probably can't do better than verification. And I don't, yeah, if you can prove that I think you can prove that verification has to take n time. And then I think, yeah, or at least, yeah. Okay. So verification is a place to start, but we're actually going to try to do even better because that's only going to give us n. Any other ideas?
Intuitively, it makes sense to me why for sorting we can't do better than verification. There's definitely a lot of problems out there where verifying it might take longer time than just coming up with a solution, right? So is it really not about to start with?
Okay. So in general, should verification be quote unquote easier? Well, okay. In this class, we'll often focus on quote unquote correct algorithms, right? So that throws out almost everything in the real world. But the algorithm should confidently always be correct, right? You say, okay, here's this problem, here's my algorithm that always works. At the very least, then, if your algorithm is correct, it itself constitutes a proof of correctness. In the worst case, I should be able to print out a transcript. Here's a log of my computer following this algorithm and outputted this thing, and this algorithm's correct. That's some kind of certification, right? So someone who knows nothing about the problem can at least check that the computer followed the instructions of the steps and verify if that algorithm's already proven correct. So in some sense, verification is always no harder because a correct algorithm should constitute a proof of correctness. Sort of a sideways answer, but that's one way to look at it. Any other ideas? Yeah.
Like any algorithm is going to do comparisons, and then in all one direction. So we want to make sure that no matter even if we have someone who's giving us the worst inequalities possible, there's not good for real work.
Okay. Yeah. I think what you're imagining is sort of like a really clever resistant adversary. And there are certain problems out there where for some reason there's some information you can only access it from like a black box. They'll call it an oracle. And I often see these lower bounds because in the oracle, you can play this duck and dive game where you keep changing what's in the black box as long as you're still fulfilling the contract of the black box. So that is certainly an approach. It's not the approach we're going to take here, but we are going to start where you started, which is we're going to focus just on algorithms that can only make comparisons. In fact, if they were bits and numbers or something called radix sort, is sort of cheating. Okay, you're only allowed to make comparisons. And our goal first is to capture all algorithms that only make comparisons. So we're just going to focus on the comparison bit of it. Maybe even does lots of extra stuff. We don't care. And okay, so all I know about some algorithm is that it makes at least k comparison queries, and I want to show it has to make at least some number of comparison queries. Okay, so an algorithm, any algorithm that's in a comparison model is going to do some comparison. It's going to choose two things to compare, get the result, smaller, bigger. Choose two things to compare, smaller, bigger. It might be adaptive. Based on your output from the first one, you choose your next comparison. That's totally fine. But at the end of the day, everything is going to be a function of your k queries. Your algorithm is going to make k queries, and those yes or no answers, is a deterministic function of those answers. Okay, especially once the algorithm is set, right? Once the instructions are set, if you just know the answers to the queries, you know what it's going to output. Okay, so each query has how many outcomes? Not a trick question. Two. And okay, so the algorithm makes k queries for some k. Each query has two outcomes. How many possible different lists can your algorithm output? 2 to the k. We're down to the last 3 minutes. You can't be too shy anymore. Okay, down to 2 to the, you have most 2 to the k possible outputs. That's without knowing anything about the details of the algorithm. Okay. Meanwhile, if you're trying to sort, if you have n numbers, how many possible lists are there? N factorial, right? There could be n choices for the first one, n minus 1 for the second one, n minus 2, n factorial. Okay, so what does that tell us about k and 2 to the k and n factorial for any correct algorithm? Yeah. All right, 2 to the k needs to be bigger than n factorial just to be able to output every possible list. Now we start to get a handle. Okay. All right. Oh, didn't go well. Okay. So the only messy part is what on earth is log of n factorial? Anyone have a slick way to lower bound this? Again, we don't care about constants. So if you're thinking Stirling's approximation, you're thinking too hard. If you haven't heard of Stirling's approximation, good for you. Yeah.
Small base 2.
Well, yeah, we want to take the log base 2, but what's log base 2 of n factorial? What's a lazy argument? Yeah.
If you say each term in factorial is like less than n, they probably assume like n to the n.
So it's less than n to the n. Only here the inequality is going the other way. So give me something equally lazy. It's at least something. One's no good. We need something better than 1. Okay. So there's at least n over 2 terms that are at least n over 2. That's better than 1, n terms of 1, right? So we can at least plug that in. That's everyone sees this inequality, nothing special. You plug that in, and you start getting that k has to be at least, n over 2 log n over 2. I don't mind the over 2 part. So you need at least some order of n log n comparisons. You can actually get this really precise, and I think you can get rid of the constants, but I don't care. Okay, you need on the order of n log n comparisons, and this is just to be able to output any possible list. Okay? In fact, I don't know if the argument is actually that hard. I think the real tricky part was just the setup. I think once you got to this thing where you keyed in on the fact that any algorithm has to make k comparisons, and from that output something, and it's a function of those return values, then the rest is sort of making the inequality and doing some arithmetic. And if you haven't seen the tricks, it might take a little bit longer, but otherwise. Okay. All right. Okay, so let me conclude. Okay, so what we've actually shown is that in the comparison only model, so this throws out things like radix sort, any sorting algorithm has to make n log n comparisons up to constant factors. Yeah. So, okay, so this is our kind of first example of duality or two sides of the same coin. So we have an upper bound, n log n. You probably knew this coming in. And we showed a lower bound of also n log n. Okay. Now, obviously, any lower bound has to be less than or equal to any upper bound. That's just by definition of lower and upper bound. But now we have the opposite inequality, right? We have some upper bound that up to constants is less than or equal to the lower bound. Okay. And that together makes them very powerful because they mutually certify each other, right? They certify each other to be optimal. Knowing that it's n log n by itself is nice. Knowing that n log n lower bound by itself is tight, but only together you actually know that they're both best possible. I mean, the upper bound is best possible. That's maybe your natural interest to get a fast sorting algorithm, but you've also got an optimal lower bound because you know you have an upper bound that meets it. They can't push up anymore, right? And it really helps to look at both sides of this coin to be able to make a very strong conclusion, right? This is saying you know everything there is to know about the algorithmic complexity of sorting in the comparison model. There's nothing left. Okay, but you need to look at both sides, the upper and the lower, to come up with such a clear understanding. Okay, see if there's anything left. Yeah, okay, n log n is the right answer. Okay, so then that will sort of be our canonical problem. Other problems, we won't often have matching upper and lower bounds. Some problems will be easier to get upper bounds, some problems will be easier to get lower bounds. Okay, and that's just part of the fun. Okay, thank you. I'll see you guys Thursday.